So far we have seen that every process will have a process control block, which means every process itself is nothing but a process control block, and it will also have some attributes associated with it, like process ID, set of all files opened by it, then program counter, all the program counter values, all these things, right? So for every process we will be having a PCB and an attributes, okay? Then the PCB and attributes of a process collectively is also called as a context, okay? Context of a process, okay? See, we have seen what a PCB is, right? A PCB will be having program over here, and then we will be having static and global variables. Then we will be having stack and heap over here, okay? Now this is what we mean by a PCB of a process. Along with that, we will be also having something called as attributes like process ID, list of all open files, and all these things, right? All these things of a particular process, say process P1, is also called as context of the process P1. Okay, so for every process there will be something called as context. Fine. Now let's come to this. Now from this we have so far we have seen that there will be let us assume there are a lot of programs in RAM. First of all we have OS, then we have P1, P2, P3. Okay, now within these three processes, whichever process should get the CPU first is being decided by the scheduler. That's what we have seen so far, right? Now that program, that scheduler is specifically called as short-term scheduler. Okay, that scheduler is also called a short-term scheduler. Okay, now that short-term scheduler will be part of our OS code. We've already seen it. Okay, now we know that from hard disk we move some programs into the RAM, right? Initially the process is being created, which means the process is in new state. Where once a user opens a program, a process will be created, which we said that the process is in new state. Now there will be a lot of processes which will be in new state, right? There will be a lot of processes in new state. Now within this among these processes, we can only move a few processes into the RAM, right? Because capacity of RAM is much lesser than the capacity of hard disk. Now among these very processes, which group of processors should be moved into the RAM? That has to be again decided, right? That is also what we mean by resource allocation. We have seen in the earlier part of our course, maybe in the second lecture or first lecture, we have seen it, right? Now this RAM is a resource which has to be given to only few processes among all these awaiting processes, right? So now which processor should be moved into the RAM is being decided by something called as long-term scheduler. Okay, long-term scheduler is itself a program which will be part of our operating systems program. Now this long-term scheduler will say among the processes which are being created inside the hard disk, which are the processes which has to be moved into the RAM. Okay, only few processes. Let us assume there are 5 processes which are created inside the hard disk, but we have only space for only 2 or 3 processes inside the RAM. Out of the 5 processes, only 2 or 3 can be moved into the RAM because the capacity of free space in the RAM can hold only 2 or 3 processes. Now, which 2 among the 5 has to be moved from hard disk to RAM is being decided by a program called as short-term scheduler. Okay, fine. Now, let us assume our RAM is full. Okay, our RAM is being completely occupied by using 4 processors named P1, P2, P3 and P4. Let us assume a new process P5 is being created. Okay, and let us assume every process will have something called as priority. Okay, we have seen it. Priority is a number which is given to every process. We have seen in attributes, right? See, every process will be given a number. Say process P1, P2, P3. Let us assume P1 is given a number as 7, P2 is given a number as 6, P3 is given a number as 3. Okay, now let us assume the process whose priority number is greater should be given the higher precedence, higher priority. Okay, which means P1 is having higher priority than P2 because 7 is greater than 6. Similarly, P1 is also greater than P1 should be given higher priority over P3 because 7 is greater than 3. Okay, so among these three processes, P1 is having the higher priority. Okay, so every process will be given a priority number. Okay, now let us assume P1, P2, P3 and P4 are having some numbers. Let us assume P1 is having a number 1, P2 is having a number 2, P3 is having a priority 3, P4 is having a priority of 4 and P5 is having a priority of 5. So now in case if P5 comes into the RAM, P5 will be executed first. Once P5 comes into the RAM, P5 will be preferred before P1, P2 and P3 and P4 by the scheduler, right? Because P5 is having higher priority than these four processes. But the problem here is RAM doesn't have any space for P5. We cannot move P5 from hard disk to RAM because the space is already being occupied inside the RAM. Now what we should be doing? What we should be doing is we should be moving one of the processes in the RAM into the hard disk, and we should be moving the high priority process which is P5 from hard disk to RAM. There is no other way. Okay, see, we should always give more importance to high priority process. Okay, higher priority processes should always be executed first before lower priority processes. So the only way to do this is we need to move one among these low priority process into hard disk, and we need to move the high priority process into the RAM. Okay, now the decision which we might have to take here is, among these four processes named P1, P2, P3 and P4, which process are you going to move to hard disk? Okay, see, we need to move one among these processes into hard disk so that we can bring P5 into in that free space which is being freed right now. Okay, now which among these four processes have to be moved to hard disk, that should be decided, and that is again decided by our operating systems, and the part of the part of OS which decides that is also called as medium term scheduler. Okay, medium term scheduler is itself a function or a module which is present inside our OS code, which will decide which process should be swapped out of the RAM so that the high priority process can be swapped into the RAM. Okay, swap out means moving a process out of the RAM. Swap in means moving the process into the RAM. Okay, that is the difference between swap out and swap in. Okay, so this moving out and bringing in is also called as swapping. See, we actually moved a low priority process from RAM to hard disk, and we moved a high priority process from hard disk to RAM, right? This process is also called as swapping. Okay, this exchanging is also called as swapping. Fine, and this is being done by something called as medium term scheduler. So what we have seen so far: long term scheduler, short term scheduler, medium term scheduler. Now, among a lot of processes, which processes has to be moved into the RAM and how many processes has to be moved into the RAM is being decided by long term scheduler. Okay, now once the processes are placed inside the RAM, which process should access the CPU first is being decided by short term scheduler. Okay, now whenever a high priority process is being created in the hard disk, one of the low priority processes has to be moved into the hard disk. Now, which among these processes should be moved into the hard disk is being decided by something called as medium term scheduler. Okay, fine. Now, whenever we are let us assume we are executing a process, when CPU is executing a process P1, okay, our short term scheduler, or simply we can even say that, see, short term scheduler, we simply call it a scheduler, no issues. Okay, because short term scheduler takes the most important decision, and that is which process should be executed by CPU next. Okay, that is very important, and so we simply say a short term scheduler. Okay, now let us assume process P1 has been scheduled by the short term scheduler to CPU. Okay, now let us assume a new process. Let us assume as of now we are having only P1, P2 and P3, and P3 is being scheduled by the scheduler to be executed by CPU. Let us assume a high priority process, say P4, is moved into the RAM. Okay, which means P4 is having higher priority than P1, P2 and P3. Okay, let us assume that. Now in that case, what we will be doing is we will be preempting P1 and then we will be scheduling P4 so that we will continue P1 after execution of P4. Okay, that is what we have seen so far. Now this process of now what we have done is we have preempted P1 and we are taking P4. Actually what we will be doing is we need to save the context of P1. Why? Because we need to continue P1, right? So we might have to store the PCB as well as attributes of P1, which we also say that as context of P1, right? Context of P1 has to be saved somewhere in our computer and then we will continue with P4. Okay, why? Because after finishing P4 we might have to continue P1 from where we left, right? For that we might have to we should have saved P1's context, right? That is what we mean by context switching. Okay, this entire process is also called as context switching, which means whenever a new process, let us assume CPU is executing P1, and whenever P4 comes into the RAM whose priority is higher than P1 has to be preempted and P1's context has to be saved and P4 has to be scheduled to the CPU. Okay, this entire process is also called as context switching, which means we are switching the context, which means initially we were having this context of P1 in the CPU. Now we are having the context of P4 in the CPU because we have switched the context. Okay, fine.